How's it going, guys, and welcome back to another 1001 MSc online tutorial video. My name is Brock Grant, and today we're going to be going through some questions involving nuclear chemistry. So let's hook into it. Okay, so some prerequisites for this module. I would just recommend going through, obviously, the first video in this series, so going through nuclear chemistry, and going through the atomic theory part, just making sure that you're comfortable with protons, neutrons, electrons, and sort of how we write them out. So we're going to be going through a handful of questions here. So questions 6, 8, 14, 22, and 38 on chapter 18. Now, if you wish to fast forward through these or choose a particular question of your interest, all you need to do is click on the annotations here, and that will automatically fast forward you to that particular question. Okay, so what I want you to do is make sure that you please pause this video and have an attempt yourself, then we'll work through it together as a team. Okay, so the first question says, write the nuclear equation for the alpha decay. So we have, and that will go to, so we know it's alpha decay. So straight away when we see alpha decay, we know that it is a helium nucleus. So if you look on the periodic table, it is 4, 2, helium. So that's what it represents. So I'm going to write that in here. And what we do is we then just subtract these numbers together. So that means we're going to have 238 minus 4, so 234, 90, so that minus 2 goes to 88. And if you look on your periodic table for the element that is number 88, that gives us ZA. And it's as simple as that. So now we have a look at the next one. So we have 23994 Pu. So same deal, we have a helium nucleus, so 4, 2, helium. And that will give us, so 239. So we subtract 4, so 235. 94, we subtract 2, so 92. And that will give us, if you look on the periodic table for 92, that gives us uranium. And that's it. So that's how we write the nuclear expression of alpha decay. Biggest things to take away from here is that alpha decay is a helium nucleus. So if you have the different types of nuclear emissions, so alpha particle, beta particle, and gamma rays, you're laughing. So let's have a look now at the nuclear expressions for the beta decay. So here we have aluminium. So we go aluminium, so we got 28, 13, aluminium. So remember that a beta decay is a neutron that breaks down to form a proton and an electron. So this can also be denoted as E0 minus 1, because it's showing that although the number of protons aren't changing, the number of neutrons are. So essentially we just write 0 minus 1 E plus, so what we do here is we have a look, so our top number here, so 28, that doesn't change. So we still have 28. However, our number of protons do. So 13, and we know that this number has to go up from a beta decay, because this is going to be losing a neutron and gaining a proton. So that means that we're going to have not 13, but 14. Now we look at the periodic table and you see which element matches 14, and that gives us silicon. And again, these still add up. So if you go 0 plus 28 is equal to 28, and 14 minus 1 equals 13. So our numbers still add up. So it's still just your normal maths, but the biggest thing is just to remember that beta decay is the breaking down of a neutron. So let's have a look at the next one, which is NP. So we're going to have 239, 93, NP. Now it's going to be the exact same thing. So we're going to have a release of our beta particle or our electron here. So that is 0 minus 1 E plus, so we still have 239 because that's not changing, but this is going to be a plus 1. So we're going to have 94 because we're gaining a proton. So if we look on the periodic table, that gives us Pu. And that is how you would solve a question on beta decay. Okay, so let us now look through question 14. So complete and balance these nuclear equations by supplying their missing particles. Okay, so what I can see here so far is we've got sort of aluminium and helium, and we've got a phosphate atom and something else. So what we do here is, again, we just do some basic maths. So we go 27, 28, 29, 30, 31. But this one only has 30. Okay, so that tells us that whatever this is has 1 up here, so with the atomic mass. And then we go 13 plus 2 is 15. But here we have 15 as well, so that means this is 0. So what this tells me is that if we have 1 in the atomic mass and 0 in the atomic number, so the atomic mass is protons and neutrons, whereas the atomic number is protons only. So what this tells me is that this is a neutron. And that is our missing particle here, is that it is releasing a neutron. Now, the next one is, again, the exact same deal. So we have nitrogen here. And what we need to do is we need to make everything balance out. So we have 13 plus 1 is 14. So that means our x must have something plus 2 that will give 14. So that must be 12. Now 7 and 0 means our total atomic number. So that means our atomic number here is 7. So 1 plus something gives 7, so that would be 6. So we look on the periodic table and we see, okay, so what's something that has the atomic number of 6 and an atomic mass of 12? And that atom is carbon. So that means that our missing particle here is a carbon atom. Okay, so let us look now at question 22. So potassium 40 has a half-life of 1.25 times 10 to the 9 years, so a long time. How many months would it take for 1/2 of a 25-gram sample to disappear? So we know that it has a half-life of 1.25 times 10 to the 9 years. So how many months would it take for 1/2 of this sample to go away? So that is 1 half-life. So all we need to do is we take this number here, so 1.25 times 10 to the 9 years, and multiply that by 12, because that's our half-life in years, so we just convert it to months. So we go 1.25 times 12, and that's going to give us 1.5 times 10 to the 10 months. And that is our half-life of potassium 40 in months. That's how long it's going to take a 25-gram sample to halve. Okay, so let us look now at question 38. So how much of a sample of cesium-137, so they've given us a half-life of 30 years, must have been present if originally, after 270 years, 15 grams remain. Okay, so this is where we need to use our formula here for half-lives. So that is, so how much of a sample of cesium-137 must have been present if originally after 270 years, 150 grams remain. So we don't know the initial amount, but we know that after 270 years, 15 grams remains. So we go 15 grams is equal to the initial amount, which we don't know, that's x, times 1/2 to the power of, now the power of is our time, so that is 270 years, divided by the half-life, which is 30. So I'm just going to simplify that over here. So I've got 270 divided by 30, and that's going to give us 9. So it means that 9 half-lives have occurred between our final and our initial amount. So what we do is we go 1/2 to the power of 9. That's going to give us 2 times 10 to the power of -3. So we rearrange this. So we go 15 grams divided by 2 times 10 to the -3 equals x. So x is going to equal 7,680 grams. So 270 years ago, we had 7,680 grams of cesium-137. However, after this time, only 15 grams remained because of the half-lives, and it kept just dividing. Okay guys, so that finishes up Module 11 Video 2. So thank you all very much for watching today. I hope you all enjoyed it. If you have any questions, queries, suggestions, feedback, anything like that, please feel free to send me an email at b.grant@griffith.edu.au. If you could all please just complete the surveys just down below for me, please, that'd be fantastic. As I said, that gives me a lot of feedback and a lot of help with the making of these videos so that I can make them a useful and productive resource for your studies. So thank you all very much again for joining me for our chemistry. So next up, we're going to start on physics. So thank you for joining me. Best of luck with all your studies, and I'll see you all next time.